2.4 and 2.5 of the Good Science Years 9 and 10 textbook. Thought I'd merge the two chapters into one because they do overlap a lot. I'm going to begin with Newton's laws. So Isaac Newton, it's worth knowing this guy's name. Isaac Newton was an English scientist. I'm going to call him polymath. Okay, he was a mathematician, physicist, astronomer, philosopher, all that sort of stuff. He was basically a scientist, but anyway, he lived in the 1600s, and his work was so important that the measurement, the unit for force, was named after him in his honor, called the Newton, capital N. And by definition, 1 Newton is the amount of force required to accelerate a mass of 1 kilo by 1 meter per second squared. That's where you get that from. Now, typically, a typical apple has a mass of around, let's say, 100 grams. All right, that's what, 0.1 kilos, because there's 1,000 grams in a kilo. And apples drop with a force of around 1 Newton. Okay, think of that. So when you have an apple weighing around 100 grams, if you drop that to the ground, that force, if you can measure it, is 1 Newton. Now, Newton came up with 3 laws of motion in the 1600s that describe how objects move in space and how that relates to forces. So there are 3 laws. Newton's first law states that an object stays at rest. Okay, stationary, in other words. Stationary means not moving, or at the same speed, unless an external or unbalanced, same thing, force acts on it. It's very important there. Okay, it's also known as the law of inertia. What does that mean? What's inertia? Okay, think of an elephant, let's call it E, and a person here, P. What's heavier to move? Well, obviously the elephant, because it's got a bigger mass. Okay, it's got more inertia. Inertia is the property of objects that tells you how hard, actually, better way to say it, an object's ability to resist motion. The heavier something is, the more mass it has, more mass it has, the more inertia it has. So if you increase the mass of an object, the more inertia it has. And this law tells you, basically in a nutshell, objects will continue doing what they're doing unless acted upon by a force coming in from somewhere. Okay? Because an object that's stationary, not moving, like a box on a table, or a box that's moving at constant speed along a table, has all the forces on it balanced. Balanced means it's doing what it's doing. It's not accelerating, it's not flying off, it's just doing what it's doing. If an unbalanced force, unbalanced here. An unbalanced force means if a force comes along and disrupts its motion, then the object will no longer be doing what it's doing. So that's Newton's first law. And objects will do what they're doing, what they're initially doing, unless something comes along, an external, an outside force that's unbalanced to get it out of its current state of motion. Suppose here's a box. I apply 10 newtons to the right and someone else applies 10 newtons to the left. It'll stay where it is. The forces are balanced, okay? Because think of 10 coming in from the right. Think of 10 newtons that I'm pushing it at is in the plus direction. The minus 10 is in the minus direction. 10 minus 10 is 0. So the forces are balanced. However, if the box is sitting there and I apply a force of 20 newtons, the forces acting on the box now are unbalanced. Okay, it's now moving. It's not stationary anymore. It's not sitting still, it's moving. Or think of something else. Think of a silly scenario. You're sitting in your chair. When you're sitting in your chair in class, hopefully you're sitting down, listening to the teacher, you're in a state of, the forces acting on you are balanced. You're not moving anywhere, you're just sitting there, stationary. Someone comes along and pushes you off your chair, that's an unbalanced force, right? Your state of motion has been disrupted. So that's Newton's first law. Newton's second law, quite simply, F equals ma. We've explored this before. It tells you need a force to accelerate an object. In other words, you can't just expect a box sitting on a table to start moving, right? You need to do something to it. You need to push it. You need to push it for it to start moving, and it will accelerate. Acceleration, by definition, is the change in velocity of an object over time. How fast its speed is changing, in other words. Okay, if you were to graph the acceleration of an object over time, if I was to shove the box rapidly, its acceleration would look like this. No, it's let's say distance. Its distance will look like this. Okay, I'm giving it a jolt, and its distance is exponentially rapidly increasing. So in other words, if I had a slow-mo camera, the box is starting here, then all of a sudden it's there, and then it's all the way there. So the distance is rapidly increasing. That's why it looks like a curve. Okay, and that's how you calculate acceleration. Change in velocity over time. It's just final velocity minus initial velocity over final time minus initial time. Okay, suppose a mass weighs, 10 kilograms, and I apply a force of 10 newtons. What's its acceleration? What am I given here? I'm given mass and I'm given force. Just do this quickly. So we need F equals ma to work out acceleration. So A is just F over m. Using algebra, 10 newtons divided by 10 kilograms, and that's 1 meter per second squared. Or you can write newtons per kilogram, same thing. But meters per second squared typically. Best to write it like that. Okay, the more mass an object has, the more force you need it to accelerate it. In other words, Newton's third law states that for every action, there's an equal and opposite reaction. Like being nice to people, right? Every day, being nice to your teachers. Okay, if you're nice to someone, they're going to probably be nice to you, most likely back. Okay, karma. Anyway, this basically tells you that forces come in pairs, right? In other words, if you want to jump off the ground, you're pushing down on the ground with your legs, but the ground also pushes you back up. Okay, that's Newton's third law. Also, aircraft. This is a common question I get asked a lot. How do aircraft keep... I'm going to draw it 2D. How do aircraft keep moving if... Okay, so aircraft, they've got it, let's say 2 engines here. They generate thrust. Okay, the force provided by the engines. The force is moving that way, to the back. But due to Newton's third law, if every action is an equal and opposite reaction. From the thrust acting backwards, that propels the plane forwards in the air. Now, people would then say that these two arrows here, these two vectors, so let's call that motion, let's call that thrust. These two arrows would be the same, right? For every action, there's an equal and opposite reaction. That means that the size of the arrows in this case are the same. So how can it be moving in a straight line? How can it be moving, in other words? Reason being is because the net forces acting on it is zero. Okay, it'll do what it's supposed to be doing, that's moving in a straight line. According to Newton's first law, object that's stationary or that's moving will continue doing so unless acted upon by an external force, an outside force. So a plane moves forward because its engines push air backwards. Okay, the air being pushed backwards, that's the action, and the reaction is the motion of the plane that's moving forwards. So you get action-reaction pairs with Newton's third law of motion. Forces come in pairs, right? If you're sitting in a chair, you have your weight force acting downwards, but you also have a normal force from the ground acting on the chair, acting upwards. Okay, these are action-reaction forces as well. Let's look at force diagrams now. This is chapter 2.4. So there are things, and engineers, if you want to get into engineering, you need to know this. Okay, you look at these in more detail later on. There are things called free body diagrams. FBD for short. Free body diagram. FBD. So suppose I have a car. So engineers and scientists, we don't have all day to just sit and draw diagrams, right? We use free body diagrams. We take this, we usually represent the car with a dot. Okay, that dot there, it's free of any bodies, this next diagram. That's why it's called a free body diagram. There's no bodies here, just a dot. And suppose I want to draw the forces acting on it. It's just sitting there on the road. The force acting down on it is the weight force, gravitational force. Weight, W, is mass times gravity, mg. Where weight is measured in newtons, mass is measured in kilograms. G is a number. It's the acceleration due to gravity. It's 9.8 meters per second squared. In other words, G is just A, but for gravity. Okay, it's got the units of meters per second squared. It's called the acceleration due to gravity. Everything on Earth has a weight force associated with it because gravity is acting on everything on Earth, right? So let's say a bus will have a larger weight force than a person because it weighs more. If you have more mass, you have more weight. Okay, gravity, the G stays the same. G is for gravity, 9.8 meters per second squared. However, there is also an equal and opposite force acting upwards on the car. Let's draw an upwards arrow. That's got the same length as the downwards arrow. This is called the normal force. Normal because it's at 90 degrees to the surface. In other words, the flat road. So this is your weight force acting down. It always acts down. Weight force always acts down because gravity always acts down. Normal force acts upwards, always, yeah? And the normal force, it's calculated, it's quite simple. It's just mg. It's the same thing. So that is a free body diagram. It's just a circle here, in this case, a dot with two arrows. Let's do another one. Let's suppose a bit more complicated. There's a guy on a bike. I'm not going to draw it. Let's say here's a bike. There's a guy on a bike. He is moving. He's applying a force to the pedals. It's making it move at 220 newtons to the left. Okay, I'm going to write force F sub pedals. Force due to the pedals. There's air resistance acting in the opposite direction at 50 newtons. So 50 newtons, that's force. I'm going to write air, force sub air. There's also friction acting in that same direction at 70 newtons. So notice here the arrows. I'm drawing a bigger arrow for friction than for the air resistance. Force sub friction. Okay, because 70 is bigger than 50 and forces are vectors. I'm using a bigger arrow. And let's suppose the weight force, the total weight force W for the cyclist and the bicycle, 600 newtons. And you need to draw a free body diagram. Let's suppose you're giving this in the exam. Draw a free body diagram. Let's do it. First things first, as the term free body suggests, it's free of any bodies. So just use you can use a rectangle too. You can draw a rectangle like this, no problem, or a dot, but it's just simpler than the original diagram. Okay, let's draw the forces now. 220 is acting to the left. That hasn't changed. Friction is, air resistance is 50 newtons to the right. And friction is 70 newtons to the right as well. So it's a big arrow. I should be drawing this to scale. This should be a big arrow here, the 220, but anyway. Wave force is acting downwards, 600 newtons. Now the normal force, we need to work this out as well. It's simply 600 newtons in the opposite direction. It's always acting in the opposite direction to the wave force. And suppose we're asked to find the net force F sub net in the y direction. Okay, this is y, and that's x, just like in BATS. You only look at the y direction in this case. So you have 600 and 600. Now, that's positive y, that's negative y, and that's positive x, and that's negative x, just like in maths, on the number plane. So the net force, the total force in the y direction is just plus 600 newtons minus the 600 newtons for the weight force, and that's 0. 0 newtons. That is your total force in the y direction. Now, what about the x direction? F net sub x. Now, it's a bit more complex. It's not really that complex. Just have to look at the diagram. Now, you have minus 220 going to the left, minus 220. Let's start from the left to make things easy. You have plus 50 newtons to the right and also plus 70 newtons to the right. Okay, because that's in the plus direction, plus x direction. On your calculator, if you do minus 20, minus 220, plus 50, plus 70, minus 100 newtons. In other words, the total force in the x direction is 100 newtons to the left, because we've defined left as being negative. So that is the same thing as saying that total force is acting that way, 100 newtons to the left. Let's do some more practice. And also just to note, the acceleration and the net force always act in the same direction. Okay, A and F sub net in same direction. Because the cyclist is cycling to the left, that means the acceleration is to the left, right? And the net force is to the left, which is minus 100 newtons. Here's another example. Suppose I have a car moving to the right this time at 100 newtons, friction at 20 newtons, weight force, actually mass is 1,000 kilos. So we need to draw a free body diagram showing all the forces here. Let's do it. Let's draw a dot for the car. Now the mass is in the force. We need to convert this to mass. Okay, the weight force is mg, mass times gravity. Mass is 1,000, gravity is 9.8. 1,000 times 9.8 is 9,800 newtons. So 9,800 newtons. Now the normal force, it's got to be the same length, same arrow, but opposite direction. It's also 9,800 newtons. Okay, there's another force acting upwards, the normal force. Left, 20 newtons, let's call that the frictional force. Right, that's 100 newtons, the big arrow. That's the force getting the car to move. And that's your free body diagram there. Suppose you need to work out the net force in the y direction. Now, taking y plus y minus y plus x minus x as follows. You have plus 9,800 acting upwards minus 9,800 acting downwards. So the normal force minus the weight force, that's 0 newtons. The net force in the x direction is, so minus 20 newtons because it's acting to the left, plus 100 newtons because it's acting to the right, and you get 80 newtons. And it makes sense. Sanity check, always do a sanity check. That means that always make sure that it makes sense. 80 newtons of total force acting to the right. And the car is moving to the right, right? So if it's moving to the right and the net force is to the right, it makes sense. It's accelerating to the right and it's moving at 80 newtons.